Have you ever stared at an image of a military helicopter and felt something was just different? You are not alone in this observation. Many people who study aviation, or even those with a casual interest, notice a distinct feature on certain Russian helicopters. Single set of blades on top, smaller one on the tail, two large rotors stacked one above the other, spinning in opposite directions. Why do so many Russian helicopters look this way? The simple answer: these rotors provide lift. But that is true for all helicopters. The real story is rooted in physics, engineering philosophy, specific demands of modern warfare. This will delve into the engineering principles behind the design choice. We'll move past the visual oddity to the complex interplay of forces keeping a helicopter aloft and controllable. From fundamentals of helicopter flight to the specific tactical advantages Russian designers sought. A common myth circulates among casual observers about why some helicopters have two main rotors. Many people assume having two sets of blades is simply about generating more power or more lift, like putting a bigger engine in a car to make it go faster. The idea is that if one rotor is good, two must be better, allowing the helicopter to carry heavier loads or fly at higher speeds. While there is a kernel of truth to the idea that the system can be very powerful, this explanation misses the fundamental engineering problem the coaxial design is built to solve. The primary purpose of the second counter-rotating rotor is not merely to add brute force. Its role is far more elegant and critical to stability and control. This simplistic view overlooks the subtle but violent forces at play when a helicopter takes to the air. The core issue is not just about pushing air down to go up, it's about preventing the aircraft from spinning itself into an uncontrollable frenzy. If the two rotors were just for extra lift, they could theoretically spin in the same direction, but this would only magnify the core problem that plagues single-rotor designs. The true genius of the coaxial system lies in the fact that the two rotors spin in opposite directions. This opposition is the secret, the clever trick that unlocks new performance characteristics and makes the design viable. To understand why helicopter designs diverge, we must grasp Isaac Newton's third law. For every action, there's an equal and opposite reaction. When a main rotor spins to push air down, it also exerts an equal and opposite rotational force on the fuselage. That force is called torque. If left unchecked, torque would make the helicopter spin uncontrollably opposite the rotor blades. The aircraft would become a dizzying carousel in the sky, unable to point or fly straight. So every helicopter design needs a way to counteract torque. The most common fix is the tail rotor. A smaller, vertically mounted propeller on a long tail boom, the tail rotor pushes air sideways. That sideways thrust pushes the tail opposite the torque, holding the fuselage steady. The pilot varies tail rotor thrust with foot pedals, which lets them keep stability and yaw. Turn the nose left and right while hovering. But tail rotors have major drawbacks. Firstly, they consume a lot of engine power, roughly 10 to 30%. Secondly, the tail boom and rotor add length and weight, making the helicopter less compact. Finally, especially for military aircraft, the tail rotor is vulnerable. It can be damaged by ground fire, it can hit obstacles like trees or wires, and it can suffer ground strikes during tough landings. With the problem of torque understood, we can now clearly compare the two dominant design philosophies. The first is the conventional, or single-rotor design. This system, pioneered by Igor Sikorsky, features one large main rotor for lift, and a smaller tail rotor for anti-torque and yaw control. It is the most common helicopter configuration in the world, used by manufacturers in the United States, Europe, and even by Russia's own Mil Design Bureau. Its primary advantages are its relative mechanical simplicity and a long history of development, which has made it a reliable and well-understood technology. The long tail boom provides excellent yaw stability in forward flight, acting much like the feathers on an arrow. The second path is the coaxial design, most famously championed by Russia's Mil Design Bureau. This system uses two counter-rotating main rotors on a single mast. As we've established, this design intrinsically cancels out torque, eliminating the need for a tail rotor. This fundamental difference leads to a cascade of other design distinctions. Without a long tail boom and rotor, the helicopter can be made significantly shorter and more compact. All of the engine's power is directed to the main rotors, which can translate into better lift performance. The deep association between coaxial rotors and Russian aviation is almost entirely due to the pioneering and persistent work of one design bureau, Kamov. Founded by Nikolai Ilyich Kamov, the company began experimenting with counter-rotating rotor systems even before the end of World War II. Kamov's early focus was on developing small, light observation helicopters for the Soviet Navy. The Navy had a specific and demanding requirement. They needed helicopters that could operate safely and effectively from the small pitching decks of warships. This operational environment made the conventional helicopter design, with its long and vulnerable tail rotor, particularly problematic and dangerous. This naval requirement became the driving force behind Kamov's decades-long dedication to the coaxial concept. A coaxial helicopter, being more compact, took up less valuable space on a ship's deck or in its hangar. Its lack of a tail rotor eliminated the primary risk of the tail striking the ship's superstructure during takeoff, landing, or handling in rough seas. Furthermore, the coaxial design's inherent stability in hover and its resistance to crosswinds made it far easier and safer to land on a moving vessel. The first mass-produced Kamov helicopter, the K-15, entered service with the Soviet Navy in the mid-1950s, cementing the Bureau's role as the Navy's primary supplier of rotary wing aircraft. The K-25 Hormone, introduced in the 1960s, became the workhorse of the Soviet fleet, performing anti-submarine warfare and reconnaissance missions. It was followed by the more powerful and advanced Ka-27 Helix, which remains in service today with the Russian Navy and other naval forces around the world. So, we arrive at the core of the question. The real reason many Russian helicopters feature coaxial rotors is not a single factor, but a strategic convergence of benefits that align with specific military doctrines and operational needs. The primary driver is the pursuit of a highly compact, agile, and survivable aircraft that dedicates 100% of its engine power to generating lift and thrust. This philosophy was born from the stringent requirements of naval aviation, but proved so effective that it was later adopted for elite land-based attack helicopter units as well. It is a choice that prioritizes performance in tight spaces and complex flight regimes over mechanical simplicity. First and foremost is the advantage of compactness. By eliminating the tail boom and rotor, a coaxial helicopter like the Ka-52 has a much smaller physical footprint. This compactness is a massive tactical advantage. It allows for more helicopters to be stored on a ship's deck. It enables operations from smaller, improvised landing zones in urban terrain. It enables operations from smaller, improvised landing zones in forested terrain. And it makes the aircraft a smaller target for enemy fire. This power density, packing maximum lifting capability into the smallest possible airframe, is a hallmark of the Kamov design school. Second is the efficiency of power. In a conventional helicopter, the tail rotor is a power parasite, consuming a significant portion of engine output just to keep the aircraft stable. In a coaxial design, this power is instead channeled directly into the main rotors. This leads to superior performance in what are known as hot and high conditions, operating at high altitudes where the air is less dense, or in hot climates where the air is less dense. With more power available for lift, a coaxial helicopter can maintain its performance, hover with a heavier payload, and climb faster in these challenging environments. This is a crucial capability for forces operating in mountainous regions or operating in desert climates. The benefits of the coaxial rotor system are significant and directly address the weaknesses of the conventional single-rotor layout. The most obvious advantage: complete elimination of the vulnerable tail rotor. In combat, the tail rotor and its long drive shaft are prime targets for ground fire. Losing the tail rotor causes catastrophic loss of control and an uncontrollable spin. Removing the tail rotor dramatically increases battlefield survivability. It also removes the risk of tail rotor strikes against trees, buildings, or the ground. Another major pro: exceptional power-to-lift efficiency. All engine power goes to the two main rotors. Higher disc loading, more lift from a smaller rotor area. This lets a small coaxial helicopter lift payloads comparable to larger conventional helicopters. The efficiency is most noticeable in hover. Symmetric airflow from two rotors gives a stable, powerful cushion of air. That makes coaxial helicopters ideal for extended hovering roles, anti-tank warfare, surveillance, rescue operations with a winch. Compactness adds tactical benefits. Use smaller landing zones, hide behind terrain features, transport more easily by cargo planes or ships. For naval operations, this is a game-changing advantage. Operate from smaller frigates, corvettes, not just large aircraft carriers. That broadens a fleet's operational flexibility and combat reach, which explains Soviet and Russian naval loyalty to Kamov designs. Finally, unique flight characteristics improve handling and agility. They can perform flat turns at any speed, even a dead hover. That lets the pilot keep sensors and weapons trained while the fuselage rotates independently. The symmetric rotor system reduces susceptibility to side or rear wind gusts, granting the pilot a more stable, controllable platform in turbulence. These combined advantages make the coaxial design a formidable, highly specialized tool for complex, high-threat environments. No engineering solution is without its trade-offs, and the coaxial rotor system is no exception. While it offers a compelling set of advantages, it also introduces its own unique challenges and disadvantages. The most significant drawback is the immense mechanical complexity of the rotor head and transmission. A coaxial gearbox must manage the power from the engines and distribute it to two separate rotor masts, one rotating inside the other in opposite directions. This is an order of magnitude more complex than the transmission for a single rotor helicopter. It involves more gears, bearings, and control linkages packed into a very small space. That complexity leads directly to increased maintenance requirements and potentially higher manufacturing costs. More moving parts mean more components that can wear out or fail. Maintaining the intricate coaxial rotor head requires specialized training, specialized tools, and a more intensive inspection schedule than conventional designs. Russian engineers have made them highly reliable over decades, but they remain more difficult and time-consuming to service in the field. That can reduce operational readiness and sortie rate, since more time is spent on the ground undergoing maintenance. There are also aerodynamic trade-offs. Excellent at low speeds and in a hover, the coaxial system can be slightly less efficient in high-speed forward flight compared to a large single rotor. Upper and lower rotors operate in each other's turbulent airflow, creating complex aerodynamic interactions that reduce efficiency as speed increases. That's one reason conventional helicopters often hold higher speed records. For missions prioritizing top speed over long range, a single rotor can have the edge. In the end, the reason so many distinctive Russian helicopters have two rotors on top is a clear and logical story of engineering meeting strategy. It is not an arbitrary aesthetic choice, nor a simple quest for more power. The coaxial rotor system, championed by the Kamov Design Bureau, is a deliberate and highly specialized solution to the fundamental problem of helicopter torque. By using two counter-rotating main rotors, the design cancels out torque at its source. That unlocks a cascade of tactical advantages critical to Soviet and Russian military requirements. Those drivers were forged in naval aviation. The need for a compact, stable helicopter that could operate safely from small, pitching warship decks made the coaxial layout ideal. No vulnerable tail rotor, smaller physical footprint, superior handling in crosswinds, not conveniences, but essentials for sea operations. Naval heritage gave the design compactness, agility, and power efficiency. Those traits later helped land-based attack helicopters in high-threat environments. Conventional single rotor and tail remains the global standard for simplicity and efficiency, but Russian coaxial helicopters show an alternative path of aviation evolution. Machines like the Ka-27K-52 are different in appearance, purpose, and capability. They prioritize hover performance, agility in confined spaces, and battlefield survivability. The trade-off is greater mechanical complexity and maintenance, accepted by engineers and strategists to gain decisive advantages. So next time you see stacked rotors, know it's a design forged by necessity, naval-honed and battlefield-ready. It's a strategic choice for compact, powerful, exceptionally agile machines. That is the simple, true explanation. Form following function in military aviation. If you found this insightful, subscribe for more deep dives into aviation design.